So yeah, thank you very much for inviting me and giving me the chance to convey some of the ideas that I developed in my PhD, and yeah, which I now intend to foster and expand in a postdoc. And that's why I'm here, to co-work with people like you who have really knowledge about many different topics. And so yeah, the basic intent of my research was to somehow analyze interactions in the climate system. And my ultimate starting point within the research group I was in was from a network perspective. So we would, in my research group, start with the gridded data sets and then reconstruct networks of interactions between different grid points, for example, which were called climate networks, and then analyze them from complex network perspectives. And I was, after some wiggling around, a little bit unsatisfied with the network reconstruction, which was based on just correlations between grid points. And I wanted to get a more solid feeling of what these links mean. How can they be related to the underlying physical mechanisms somehow? So still, I start from the data analysis viewpoint. We have a complex system. We have some data given, and then we are interested not really in the interactions between individual grid points, because they are not so physically interesting often, but say we have some indices that are often defined as averages over some climatological variable over some region, but they can be defined in any way, of course. And then we go from this collection of 10,000 data points and time series to this more subprocesses view, where we are now given something like the North Atlantic Oscillation or other climate indices which represent relevant subprocesses. And now my goal is to really go from correlations between these subprocesses to some notion of causal interaction from a statistical perspective. And the overview of my talk will now be this round here. So we start from this complex system, then there's some way of defining subprocesses. I will then talk about this causal reconstruction between these subprocesses, reconstructing really a network with some causal notion. And the next step will be to quantify, to really determine what's the influence of changing a variable here on the other ones, what are pathways in this network, everything that is somehow more not really visible here, where it's just there's a link or there's no link, and here the links have colors, so there's some strength of a link. And this I will then show can be used in an hypothesis testing framework for like smaller sets of nodes, or we can also do some explorative analysis, which has been done in my group a lot, like determining somehow a notion of the importance of certain nodes. And this might not be so relevant for many climatologists actually, but from other perspectives. Okay, the first step is the causal reconstruction. And causal interactions implies, just very simply, if you're, for example, given a true causal interaction graph that looks like this, with the black lines here, and the numbers, for example, denoting a lag, a time lag, because we have time series, we have dynamical interactions. And then, for example, if this subprocess here drives with a 1 month lag or so a variable x, and with a 2 month lag a variable z1, then what this implies a correlation between x and z1 of 1 month lag. And this is a spurious link in the language of causality. So it doesn't mean that something that originates here influences something here. It's just really a common driver. And this is one way of having a spurious link in such a network. The other way is that, for example, here x is connected to y via 2 different or 3 different paths, actually. So this is not a direct interaction, but because we have included some other subprocesses in the analysis, we can determine how does the interaction, how does the influence of x on y take place, via which nodes does it go. And this is, another way of seeing causal interactions in an indirect way. And this is very important for the second part of my talk, where I want to determine pathways of interaction. And I will give examples to make this more relevant for climatology applications. So this is kind of already looking, it's a network perspective, but the same representation is given here, which includes the time structure of a process. Because we have dynamical processes, we cannot really determine the pathways of a mechanism in this representation so easily, because we have to acknowledge that each process here also depends on its past time step, which is something like processes are autocorrelated. The temperature of the last day determines the next day, and so on. So, and this is so better, not better viewed, but better analyzed in this view, where we just represent each of these processes here at each instance of time, and then a path would here go in space and time through the system. So this is really the spatiotemporal causal paths that I'm interested in. And the theory behind here is graphical models by Lauritsen, for example, big guy, or Eichler has developed a lot of these time series graphs. Okay, so this graph first needs to be estimated from the data, which is a problem of causal discovery. And I didn't show the defining equation here of these graphs, which is rather technical, but it is defined as a conditional independence relation, conditional on the whole rest of the data set, and this is not easily done statistically because it's the curse of dimensionality, especially when we want to investigate associations that are not purely linear, but my whole PhD was basically on nonlinear interactions. And this problem is not so easily solved when you have high dimensions. So this is really the curse of dimensionality that is a problem. So what I use here is a PC algorithm, which is one of the first causal discovery algorithms, which comes from machine learning community. These are very big guys here working at Carnegie Mellon University, and it's named after their first names, which it's just their way or. And the basic idea of this algorithm is as follows. So it's given a causal graph with the true links given by these black arrows. The algorithm starts with just with pairwise dependencies. So it measures, is there a dependency between Z and Y here, for example? And because of these two causal paths, yes, there is one at a lag of 3 here, just the sum of these two lags. So in the first part of the algorithm, you would measure that, yes, there's a dependency between these two. In the second part, then we, for example, another dependency exists between these two because of this being a common driver that affects both. The next step of the algorithm then tests conditional independencies. So here, for example, we test whether there's a conditional independency between Z and Y given X. So we test whether the interaction, the association between these two variables was due to this in the middle. And of course, we don't know whether it's in the middle. So the algorithm is just testing whether there's a relationship. And here we would see, yes, there's still a relationship because we haven't excluded this path here. There's still a relation between Z and Y given due to this interaction. But we don't know it. So the next step we test, okay, maybe the interaction vanishes if we, or they two become independent if we test on conditional on this variable. And also here it would not help. And only after some tests, the dimension is increased, because increasing a dimension is always the statistical problem because of dimensionality. And then we would here see that, okay, Z and Y are conditionally independent given these two nodes. And then we remove the link and have, starting from a fully connected graph, iteratively removed one more link. The same would be valid for these two. We condition here just on this node, and then it would be removed. And so iteratively we remove all these links until we cannot remove links anymore. For example, here we tested already the two remaining possible and intermediate processes, and it's still there, the link between, for example, these two. We would test whether it still exists conditional on these two, and if the conditional independence is still there, then we do not remove this link. So the convergence criterion here is once we cannot increase the dimension of the conditions anymore. Okay, so these conditional independence tests here can be performed in a linear way using partial correlation, which I guess it's a common measure also in climate analysis. I've seen a lot. And so I've applied it in this linear framework in my article in Journal of Climate. And my original PhD thesis was more about this information theoretic framework where you really get also nonlinear interactions. But there's a lot of problems with, you need to have a lot of data to basically estimate these nonlinear dependencies. Okay, the assumptions of such a method are that the time series need to be stationary. We assume that the noise that drives different components is independent of each other. And there's some more technical condition here, which says that if there's a mechanism between x and y via this path and via a direct path, and these two exactly cancel out, like, I don't know, temperature driving pressure via rain or so, and via another mechanism, which is in the opposite correlated direction. So in the end, there's no relation anymore, or it's weakened at least. And so if this is totally cancelled out, this would be violated. And finally, we always have to be cautious about how we interpret the resulting graph if we have not included other relevant variables. So ideally, you include all relevant variables. And the applications of this method are various. So one of the most important, I guess, for climatologists is maybe hypothesis testing. So you have an hypothesis idea, and I will show one example of this. Other examples are you can use it for variable selection, selecting the most important variables to predict a certain variable, for example. And I use this in a prediction framework, for example, in a paper. But I will now come to this quantification of causal mechanisms topic. So what I analyzed in the Journal of Climate papers, given like 3 time series here from the East Pacific, Central and West Pacific, and knowing that the Walker circulation here should give somehow a causal loop between the 3, can I find this from the data alone? And yeah, I don't have to tell you the mechanism. When you look at lag correlations between these 3 variables, so this being surface air temperature, and pressure over the Indonesian archipelago, then you find that everything is connected to everything. So in particular, if you look at the lagged correlations between all the variables, everything is connected here. And some with a higher autocorrelation. And now this algorithm would look at each specific link here. And for example, if you concentrate on this link from the East Pacific to the West Pacific, so this link here, then the correlation between the two in the first step would be very high. So the first step, yeah, it's just a correlation between the two. In the next step of this algorithm, we compute a partial correlation. And the algorithm would do that in a smart way. So we take one of the lag correlations towards the West Pacific, which has the highest correlation in the previous step. So that would be, for example, the lag 1 term. So we condition out the effect of the West Pacific at 1 lag. And then we still get a very significant correlation. In the next step, we consider, okay, maybe another, the second largest, for example, which is here possibly the Central Pacific. Maybe this explains this correlation between the two. And then it gets much weaker. And finally, we increase the dimension. And if we include both of these as a condition, then we see that this becomes very small. And depending on your significance level, it's insignificant. So then we remove this link. And we found that, okay, there's a correlation between the two, but there's no dependency if you exclude the influence of the Central Pacific. So from this picture, via this purely statistical analysis, we then arrive at such a graph, if we do that for all the links in the graph. So this very much, I think, yeah, resembles the causal loop of this Walker circulation, with this East Pacific here driving the Central Pacific at between 0 and 1 lag. So at 0 lag, I wouldn't talk of a causal influence, but climatological insight tells me that it's this direction. And then this indirectly drives the Western Pacific. And this other links here, they didn't get removed in this process. So what we learned from this is that the influence of the East Pacific on the West Pacific must have gone through the central surface Pacific, while the other links didn't get removed, so they must have gone via some other path. And we know here that it's via the troposphere. So,
were you looking at rainfall?
Also, this is surface pressure. And also, this is surface air temperature. Here it's pressure, and here it's also surface air temperature. So yeah, but the same result you get if you take different variables, for example. Yeah, here I choose temperature because they are very much autocorrelated, which gives even more problems in the peak width. Like you could think it's okay, they are related at lags up to 9 months or so, even though the actual relation is just 1 month here. So this is more a proof of concept, I would say. So this is now has been this step, the causal reconstruction, and now I will tell you about how we can make even more refined statements about causal mechanisms in this graph by really looking at the strength of links and the pathways of interaction. So this is strongly influenced by this book of Judea Pearl, who is a pioneer of this, bringing causal thinking to statistics and to mainly actually the social sciences. So how do psychologists, economists think about causal relations has been strongly influenced by Pearl. And his main thought experiment is that of what happens if we change, like manipulatively, if we change a variable x here, what's the effect on another variable? And this is kind of the paradigm of experiments. And he also was then interested in under which criteria, under which causal graph can we then estimate the causal effect on another node purely from data, which is what we are interested in here, because we don't want to manipulate the Earth at least too much or controlled way. So this is for this data analysis paradigm. He gave criteria for this. Okay, but what he defined is based on here standardized regression. So I use it in a linear framework again, and so what the path coefficient measured, which is actually quite an old theory from the 1930s by Stephen Wright, who used that in agricultural research, and Pearl now generalized this. But here I use the linear framework. So a path coefficient is simply given by the regression of here a variable W2, for example, on its parents in the graph. So denoted by a P here are all the nodes in the graph that have a direct link towards W2 here. So these are the causal drivers. And this coefficient alpha now has the meaning that if you raise the variable x by 1 standard deviation, then it has an effect of alpha times the standard deviation of W2 on W2. So changing x will then change W2, and holding these fixed. And this is a quantifier for a direct link. Another one is a quantifier for indirect path. For example, if we consider here the influence of node x on y, and there's no direct influence, but there's here, for example, 3 different paths. And if we denote here these coefficients, the path coefficients of the individual links, then we can decompose the causal effect of like changing x by 1 standard deviation on y just by the product, by the sum of the products across all these paths. So it's like one path is alpha times epsilon, the strength, plus beta times gamma times epsilon plus beta times delta. And this is really a nice way to decompose the causal effect of one variable on another. And you can also ask, what's the mediated effect? So how much is either of these 2 nodes? So in the previous slide, like this is the indirect effect of x on y. How much do either of these contribute to this? Like which mechanism is more important and can then be related to physical phenomena? So this can be also done by this difference of partial regressions. And in this case, this would just be the effect via the node W1 would just be all the paths that go through this node. So this would be just these 2 terms. Okay, so now I come to an application of this method to, as I said before, there are different methods of getting from this gridded data sets to subprocesses. And here, with our Czech collaborators, we use a Varimax decomposition. I'm not sure, it's similar to PCA, but it yields more regionally confined processes, which is advantageous because this is probably more likely related to subprocesses. For example, here, these are the loadings of several variables. Altogether, there are 60. Here, for example, this is a sea level pressure. So this is very much related to ENSO, of course, and this being the eastern part of this ENSO oscillation, and here this pressure component being more the uplifting western limb. Then we have, for example, here a dipole component being very much resembling the North Atlantic oscillation. So it's an objective method, and still it recovers several of these phenomena that you would otherwise have defined maybe as a difference between two different measurements. But here I just use these to reconstruct the causal dependencies between these 60 nodes. And this is weekly data, so I'm really looking at atmospheric timescales here. So just the number 60 comes from a significance test that rejects components that merely represent noise according to a criterion that computes surrogates. So maybe the component number 61 would be scattered loading everywhere and merely represent noise. Of course, the dimension is the same as the original data set, like in PCA, but it's by a significance testing. So we ended a finite set of components. But of course, this is just one way to get at subprocesses. The causal analysis can be conducted on any expert-defined set. Okay, then we use these 60 and reconstruct, using this algorithm, the linear causal network. And because there's quite some significance testing involved, and I wanted to get a more explorative way of analyzing this, I compute these path coefficients for each of the links, and then I threshold the density of the network and analyze this network at different link densities. So only the strongest links are the strongest 15% of the links I keep, for example, and then I vary this and check the robustness, because it's really important to check robustness for this kind of analysis. Okay, so coming to an hypothesis testing framework here, I show you the network here of just these 4 nodes. So I do not show all the links that enter these other processes from other components. This is just like a subgraph of the bigger graph. And the coloring of the links here is according to this strength of a link, this path coefficient. And this implies that here, raising the pressure component number 1 here, which you've seen was in the East Pacific, by 1 standard deviation has roughly, I don't know, say 30% change in the other direction of this component here. And then we have a strong positively related influence on number 32, which I should have shown you before, is this component here, just west of India, representing the pressure west of India. And Vladimir Petrukov, my climatologist, told me that this is strongly related to the Indian monsoon as one way of influencing the Indian monsoon. So that's why I maybe somehow too boldly say this is one path of how ENSO influences the Indian summer monsoon. There's many other, of course. But just within the pressure system here, another hypothesis would be via the East Asian pressure. And one can see here that these are very weak, these 2 links. And when you then analyze how much of the effect of here, number 1 or number 33, was mediated by either of these 2, then we see that the largest part is mediated via this Indonesian, or the archipelago, the East Indian Ocean, and almost nothing is mediated via East Asia here within this pressure system. So this is the conclusion we can draw from this, and this gives some insights. Firstly, that the direct effect here is very small. This is an important mediator of this influence, and then this allows to somehow go into a certain direction of which physical mechanisms are really relevant, which is then the ultimate goal. And I would say that this is one way of a more rigorous definition of these atmospheric teleconnections, which, yeah, is previously or usually it's just a highest anti-correlated value, and this gives you really a more, yeah, what pathway does such a teleconnection take? So this is still under preparation because, yeah, there's some details I'm still sorting out. So now I've shown you this, and the last step I want to show you is more an explorative way of not analyzing individual mechanisms here, but somehow getting a notion of how important is any of these subprocesses in driving others. How strong is the causal effect of each of these subprocesses on average on the others? And if you do this, then, for example, looking at the influence of this node number 0 here, that the uplifting arm of the Walker circulation, we see at a 1 week lag, for example, these nodes are significant at a 1% level influenced, and the coloring of the nodes gives the strength. So we see this link like before. We also see like a feedback on the East Pacific, and this then decays after 2, 3, 4 weeks. The causal effect becomes weaker and weaker, and if we now do this for each of these nodes, then we get a picture like this. And here I colored the outer ring, the darkness of the color, according to the average effect on any other node. And the inner color is how much is this node driven by any other node. So this is like the in effect and the out effect, which is like how susceptible is the node. That's the inner color. And if you look at the distribution, then the distribution of the incoming causal effect is very broad. So many nodes have like, or the distribution is broad. And if you look at the outgoing effect, then you see that these components in the tropical oceans here, in the Atlantic, in the node number 0 that we've seen, these 2 parts of the Walker circulation, and in the Western Pacific, number 18 is here. These are the strongest drivers of, so this is, one has to be cautious because it's an explorative analysis, and we just consider the average effect on any other component and not distinguishing whether this is relevant for a certain question, but this is explorative. So one can see some things here and then look further into hypothesis. So I've just taken here this view of the Walker circulation, the global Walker circulation. So the components that are most strongly affecting others are quite located in these uplifting regions, and also here in the Atlantic. Apart from the East Pacific, which is usually a region of downdrafts in the atmosphere, but you know that it changes. So that's one thing. The causal picture changes during El Nino events, where then these directions reverse. So my analysis here really took the whole data set, not distinguishing different seasons, which is one way of further generalizing or further developing the methods. To look at what's the winter network, what's the network during El Nino season, and so just 2 small conclusions are here. We see these strong uplifts, which are represented via the strong causal effect, and another one, for example, is that the NAO here, I've not seen many causal links going in, so it seems not to be driven a lot by other pressure components. And I did not really look into this further, but this is one way how an explorative analysis can stipulate other research ideas. Okay, so summarizing, I've shown you how a sea level pressure data set here can be decomposed with a Varimax into a selected set, into a set of regional subprocesses. I reconstructed a causal network. Then I've shown you an hypothesis on an individual mechanism within this network. And then I showed you some exploratory analysis. And all this can be computed by a Python script that I've developed with a graphical user interface to also have non-computer geeks enable them to use this framework. And last, what I wrote in my this is my foundation that gave me, or that will give me the money if I'm at an institution. What I wrote inside this proposal was like, can I extend this causal interactions to extreme values? Like before we've investigated how much is one process driving the expected value of another one, but a frequently asked question is like, okay, how extreme events are attributed? How are other processes driving extreme events, which are often much more important for humans? And another question is that dynamical processes have different time scales. So why can't I try to improve this method to take into account, for example, the causal interactions between the high frequency component of one process on a low frequency of another one. So separating the scales, which is very important. And yeah, bringing this together with this causal thinking that Jediah Pearl started, and applying this to the Earth. That's my intent, my intention for the postdoc. And with this, I thank my collaborators a lot, my supervisor, and these are just the most important references. Thank you.
Yeah, so really interesting. And sorry I was a little bit late, so I might have missed it at the beginning. But it seems that a lot of your lags were very close to zero. They of course, they have to be integers. So the lag can only be integers.
Yeah.
So to what extent is this sensitive to the time resolution of your data set?
Yeah, that's a good question. So it's the decision of the researcher what resolution you start with. So I used monthly data mainly because most climate researchers use monthly averages. Then in the last application I used weekly data because I'm also unsatisfied with all these lag zero interactions and I want to resolve them causally. So I used the weekly time interaction. And if you go to days, then the problem is that if you want to have still like the time scale of 1 month, then you have 30 lags. And then you have each node with 30, like replicated 30 times. And this is just statistically very difficult because you have a multiple testing problem. You just have a lot of links that are spurious because you did too many tests. And you would have to adjust for that, and it's difficult. So I want to adapt the time resolution just right where it's important and not too much.
But it might be because what are you doing exactly with lag zero correlation? You're not using those, right?
Yeah, here.
In that case, there's a direct link between the Central Pacific and India, but that your time resolution is at lag zero. But it might be very strong link. But if you go to daily resolution, suddenly it doesn't go up as a lag thing, and suddenly is a causal relation.
Yeah. Yeah, it is the notion of, like, I call this contemporaneous links. So this is incorporated into this framework. So yeah, you would just have here a link here, and you can also use this algorithm to recover these. I'm just hesitating to interpret them causally because they could come from an unobserved common driver. But yeah.
Sort of following on that, a lot of these sort of standard teleconnections you can think of as a propagating Rossby wave.
Yeah.
Now you would only see the propagation on a few days time scale.
Yeah.
Whereas actually but the thing exists on many months time scales, but you would have to mix the time scales a bit to see the development of the pattern.
So you mean I would use a daily time scale, but the Rossby wave evolves only after.
So if you have flaring of convection in the tropics on a longer time scale, anomalous, then from that there would be a stationary Rossby wave that with a group velocity going out like that.
Yeah.
So the pattern is set up sequentially, but then as long as this persists, that pattern will persist.
Yeah.
So the cause is here, but you'd only see it from the sort of daily time scale.
Yeah.
So I was wondering something about the PNA pattern, for instance, with Pacific North America.
Yeah.
You might have trouble seeing, it would be interesting to see what you've got from your sort of analysis, but I think the more it's set up on those time scales, you might have a problem.
This daily, but you said, so the whole phenomenon of this Rossby wave exists for 4 months or so.
Well, as long as the anomaly exists in one place.
So if I analyze just this 4 month period, for example.
You would see this at zero. You would see the relationship.
Yeah.
It would be almost zero.
Yeah. No, but if I use just by expert knowledge, I know this this anomaly persisted for a certain period, and then I use a daily resolution of, I don't know, some different components. Then I.
You could get it, but you might have to mix the two.
Yeah. Yeah.
I was going to ask you that you require data that's fairly smooth. You're using surface pressure mainly. That's, the spectral characteristics. It's a smooth field.
Yeah.
And you clearly need many realizations in order to try the various linkages.
Yeah.
I just wonder how good it would be with other variables, because actually when you're talking about these vertical circulations, and a lot of the interesting things would not show the surface pressure, for instance.
Yeah.
They would be in variables that actually have are rough fields, that they have more structure.
Yeah.
How sensitive is this whole thing to the smoothness of the data? And,
wouldn't this be more related to which subprocesses you actually take? Like, how do you define these?
well, yes, but suppose you define them in terms of a field like, the ultimate would be vorticity. So it's immediately is a very finely structured field.
Yeah.
You might define it in terms of vorticity in one region,
Yeah.
but its behavior is going to be less smooth in some sense over space and time. So if you added noise to your data, how sensitive would the whole process be?
So it very much depends on which measure of association for these condition independence tests you use. If you use just linear, you might miss out, if I get it right, some nonlinear structure that is determining the interaction between different variables. So it's maybe also how you transform the time series before you do the whole analysis. Maybe you have a time series that is, for example, rain. It's only positive, which is not very nice for correlation analysis. You transform them before to make them more normal. So there's these kind of steps are certainly very important to really construct variables of which you can reconstruct causal interactions and of which you're also interested in. So it's not a black box, of course. So you need to
nurse.
The hypothesis need to be really nursed. Yeah.
I'm more interested in the methodological aspects of
Yeah.
climate. I don't know anything about climate. I don't know much about the methodological side either. But I have two questions. One is, how reliant is your method on the original algorithm really working as it should? Because the Gleim-Morse-Bertis algorithm has been criticized quite a lot. And I'll come to my second question.
Yeah. So I use this mainly in this nonlinear framework, because in a linear framework there's other methods how you can reconstruct these graphical models, and I want to do that also because, like in a Bayesian framework, you can do this with the confidence bound and all this stuff. So there's a debate between these constraint-based algorithms and these score-based, and for me this algorithm was the only choice for this information theoretic approach, because you cannot write down a model if you are willing not to assume a model, but just estimate this conditional mutual information from the data. So that's why I was starting with this, but I don't see it as the ultimate way of inferring causality, especially when you have only in mind a linear association. And also because, as I said, in a Bayesian framework, the confidence of such a network can be better assessed. So what I've just briefly said here is, like, you remove iteratively each link, but because you do tests for one link with different conditions and you do not know a priori how many tests you do, you cannot correct with a Bonferroni or so in advance. So what I do here actually is I reconstruct only the causal parents with this algorithm, and then I test each link once more. And then I have only... So I do a variable selection with this algorithm, then I reconstruct, and then I just test every link once.
So you're not really relying on the algorithm totally. You're
No.
kind of... So if the algorithm misses something, then you'll miss it as well. But if it's a false positive, then...
No, either way, I'm testing each once more. So a link that is not one of the parents could still appear, and the other way around. So, but still, it depends, of course, on the variable selection by this algorithm.
Okay, my other question is your use of the Verimax decomposition or like it. Have other people used that in other applications, not in climate science, because it's...
Oh, yeah, in brain research, I think people use it. But this has been really due to my collaborators here. But they've, I think this article is one of the first to use that. Oh, no, it's not. I mean, Varimax is known in climate. But their original contribution was to truncate it at some point to get a dimension reduction. So that's their contribution. And, I mean, Varimax is old, of course. It's 1958.
Oh, yes,
Yeah.
It's the application.
It's the application and the significance testing for noisy components that they developed. And here, here it's the details, of course. Yeah.
Yeah, I can ask one more. So the framework that you now propose is that you create this network and then you test that network and then you go and put your physics hat on and think about what kind of climate physics is behind it, or climate dynamics. Would it also be possible to put the climate dynamics, the part that you know that you're very confident about, for instance, Rossby wave propagation speeds, to put that before you even test the network, so that you're sure that, oh yeah, I wouldn't even know what really the advantage is. It would be kind of interesting to think about doing it the other way around.
Which you have, I think, with the ENSO, what you have done it the other way around, really. With the El Nino, you chose those.
Yeah. This is the hypothesis. And actually what the framework that Pearl here developed is really not about causal discovery. Like the Spiritus guys are about how to reconstruct this graph. Pearl says, okay, there's some hypothesis. Experts know, they draw some graph and then they use this to make tests. Okay, now hypothesizing this graph, can I estimate the causal effect of X on Y? And they would put here so-called latent variables, unobserved variables, and these then lead to the problem that some effects you cannot determine from the data because there's unobserved variables. And they are, of course, also in my problem. And this has to be included. So actually, I should have maybe, if you use, for example, not only pressure, but only temperature data additionally, then you get also a big common driver, or, I mean, there's millions of variables that you can include. So you always have to interpret it with respect to what you studied. And this kind of thinking is really what this deriving hypothesis and then thinking, okay, which causal effects can I really test? And he's really from a policy advising also framework, like which policy, because there's really matters what happens, and changing one tax or whatever, and whether you can derive from the data what effect it is going to have. So I'm kind of mixing these two, and one has to be cautious. That's very true. Yeah.
Well, that's really interesting. I mean, I think this using the data and iterating with the physics and with simulation.
Yeah.
And providing hypotheses, and that's a really fascinating area. And developing the timescale thing, you talk about the transients, etc., and the time fires, and you think of the storm track, the eddies, and the Atlantic or something.
I mean, still I'm assuming stationarity when this time, but if you have, you can also go from sampling from the time to model ensembles, and then you can resolve also like transient phenomena with the CMAP5 or whatever, just 10 model.
That was really interesting.
Thank you.
Very much. That was really helpful.